Evet. Geçen ders connected space'lere başlamıştık. Şöyle kabaca hatırlatayım. Alright, so last time we defined connected subset. A subset is called connected if it can be covered by two open sets, so that these open sets do not intersect over E. Okay, and if we have two open sets like this, we call that a separation for E. And if E is not disconnected, we say that E is connected. And if E is the metric space itself, then we say X is connected or X is disconnected, depending on whether you can find such open sets or not. All right, and then we showed that this interval 0, 1 in the metric space real line with absolute value metric is connected. And then we showed that actually intervals are the only open subsets using this result. You know, image of a connected set under a continuous function is connected. We proved this. And then we proved another fact that if you have a family of connected subsets and if they have a common point, so if the intersection of all of them is non-empty, then their union is connected. And then we proved that any interval is connected, and actually the only connected subsets of real line are intervals. We proved this. We proved the intermediate value theorem. And okay, we showed that if you have a connected set, anything between the connected set and its closure is also connected. And finally, we defined path connected spaces. Path connected means that between any 2 points of the subset, you have a path joining these 2 points. Okay, continuous path. All right. Actually, let me show this. Any path connected subset E is connected. Okay, why this is true? So we assume the following: E is a subset of X is path connected, and we must show that E is connected. Okay, so that being path connected is something stronger than being connected. Why this is true? Let's see. Well, okay, assume on the contrary that or let me do it this way. Let x0 be a fixed point. And x is any other point. Well, since E is path connected, connected. There is some continuous path gamma from an interval, let's say AB, into E, well, into X, but the image lies in E, so that one point of this path is the point x0, and the other end point of the path is the point x. So we have something like this. Okay, here is my interval AB and my subset E. Okay, and here is my function, continuous function, which is from, okay, so this is x0 and this is x1. Okay, so there is a path joining this point to this point, and its image lies inside completely in E. Well, if this is the case, then we know what? Since AB is connected, this interval as a subset of R is connected with the absolute value metric, of course, and gamma is continuous, its image, so gamma AB is connected. Okay, but you know, these paths, so maybe I can do this. There is a path joining these 2 points. Let me label this path by x. Okay, so for each x, I have such a path, and let me call this set, if you want, okay, ax. Okay, so I define this set ax. Clearly, both x and x0 belongs to this set, right? Because they are just the endpoints. So ax is the subset, okay? The image of the path. Path is the function. Its image is the subset ax. Well, we have what? The subset, these subsets clearly contains the point x0. Therefore, their intersection contains this point, because all of them contain x0. Therefore, the intersection contains x0. Therefore, this intersection is not empty. But by the previous fact, and they are all connected, since each ax is connected, and the intersection of all of them is non-empty, we have what? We have the following. Their union is connected. But what is the union of these? Well, you see, these paths are all subsets of, right, E. Therefore, their union lies in E. So I have this union of this axis, while x ranges in E, is a subset of E. But E itself is a subset of 1-point sets. and each one-point set is an element of AX, right? Each X in E belongs to AX because it is the end point of the path. Therefore, I have this. So what we see, this union is a subset of E, but E is a subset of this union. So all these inclusions must be actually equality. It follows that E is equal to this union. But we have seen that this is connected. And this finishes the proof, right? Our aim was to prove that E is connected. So the proof finishes. Since the union is connected, we are done. Okay. Any questions so far? This proof is a little bit different than the one in the book, but doesn't matter. I mean, you have two proofs. Okay. So a path connected subset E is connected. We will see later that remark uh, there are path connected subsets of R2 with the standard metric, okay, well, D2, let me say, which are not path connected. Actually, let me give you one example. This is known as topologist sine curve. It is the following subset. So let E be this subset. The points 0, y in R, namely the y-axis, right? Union points like this, x, sine 1 over x, and x is a positive number. So this has two parts. One part is the maybe I do it like this. One part of this set is the y-axis, and the other part is the graph of the function sine 1 over x. And this graph has image something like this, okay? It is the sine function basically, but the whole graph is just squeezed into this, finite interval, so that this graph goes infinitely many times up and down, okay? So it will go infinitely many times up and down. And E is this red subset, the x-axis, the y-axis plus this sine curve. Maybe I'll use a different color for this. Okay. Okay, let me prove this. Let me prove that E is connected but not path connected next time. So, and meanwhile you think about this. E is connected but not path connected. Okay, I'll do this next time. Okay. All right. We proved that any arcwise or pathwise connected subset is connected. Uh, remark arcwise connected equals pathwise connected or path connected. Okay. Different authors use different adjectives. Okay. Okay. Now let's see some examples of connected subsets. Sorry, path connected subsets. One of them is this. A convex subset of Rk is connected is arcwise or pathwise is pathwise connected, and thus it is connected, and hence Rk is path connected or pathwise connected because it is convex. A ball in Rk is pathwise connected. Therefore, it is connected. All right. So let's prove this. Let E be a convex subset of Rk. Convex means what? By definition, convex means any 2 points in E can be joined by a line segment lying completely inside E. So convex subset is something like this. No, not like this. Okay. Maybe I should. Yeah, this is convex. Whenever you take 2 points, okay, the line segment joining these two lies inside E. So this is convex. Convex subset. But this thing is not convex. Okay. So this is not convex. Why is that? Well, you see, if you take this point and this point, x, y, then the line segment joining these 2 points doesn't lie inside E. Okay. So this subset is not convex. So let me remind you the definition, mathematical definition. Recall that a subset E of Rk is called convex if, okay, whenever we are given 2 points x0 x1 in E, there is the line segment let me say gamma given by this. So these points are in Rk, therefore I may regard them as vectors, so I can write the following. This is just 1 minus t0, 1 minus t times x0 plus t times x1, okay, has image in ek, in E. Note that what is this? This is just a line segment, and you see when you plug 0 you get x0, and when you plug 1 you get x1. So this is the line segment joining these 2 points. Or okay, maybe I, all right. Okay, let me change this. x0 x1 x0 x1. All right. All right. Now, why this is path connected? Well, by definition, this is a continuous function. Clearly, gamma t is continuous, and it joins x0 to x1. Hence, E is path connected. Okay. Clearly, you know, Rn is path connected. Rk is path connected, is convex. I mean, because this line segment already lies inside Rk, right? Is convex, and path connected. So the only statement left to be proven is this: a ball in Rk is path connected. Let's see. Finally, let E be a ball. Ball in Rk. So we have this. Okay. And I claim that this is path connected. Well, why is that? Whenever you have 2 points, okay, yeah, maybe, okay, let's say x1, x2, the line segment joining this 2 point should lie inside this ball, right? Well, why this is true? Okay, so one has to prove the following claim is this: if, okay, claim is this: if x1, x2 are in this ball, then gamma t, which is 1 minus t x1 plus t x2, is in this ball for any t between 0 and 1. So gamma t is a point here. Okay. When you plug 0, you are at this point. When you plug 1, you are at this point. So I claim that this lies inside this ball. Note that, of course, note that the claim shows that this ball is convex, and thus is path connected. Well, why this is true? Okay. Why any point here has okay. Let me leave this as an exercise to you. You have to just write down the metric. So distance between x0 and gamma t. Okay, what is this? Suppose this is just x0 is the point, let's say, with coordinates AB, and gamma t has coordinate, okay, coordinates AT, BT, and this distance is then what? Okay, AT minus A, alright, maybe A0, B0, squared BT minus B0 squared, okay, and you need to show that this is less than R, provided that the endpoint lies in R. Okay, what are the coordinates here? AT, BT. Suppose x1 is just a1, b1, and x2 is a2, b2. Then this is just okay, 1 minus t times a1, b1 plus, sorry, t times a2, b2. So what is this then? Gamma t is just okay. 1 minus t a1 plus t times a2, 1 minus t b1 plus t times b2, and then you have to subtract a0 b0 and take the square and so on. Let me leave this as an exercise, okay? Exercise. Finish the proof. Of course, you need to use the following fact. These 2 points, lie inside the ball, okay? You may think that, why, something like this, we need to prove something like this. Well, the reason is that, of course, it is clear from this picture, but, one has to be able to prove this using the definitions and so on, okay? And actually, this is true not just for the metric D1 or D2, but for any metric. Finish the proof. Actually, this is true for any metric, metric dr or d rho. Okay, rho 1 and infinity, including infinity, for all the metrics. If you do the proof for D2, you will see that it works for D rho also. Okay. So we have this. Okay. Okay. Now I will define connected component. Okay. Now for any 2 points, okay, let x, y be points, arbitrary points. We define in relation. We define we say that x and y are related, and write x is related to y if what happens if there is a connected subset E of x containing both x and y. So if there is a connected subset, okay, of your space containing both points, then we say that x is related to y. We first claim that this is an equivalence relation. This is an equivalence relation. Well, for this to be an equivalence relation, it has to satisfy 3 axioms. What are those? For any point x, x should be equivalence relation on x. For any x, x should be related to x. Okay, reflexivity let me write reflexive. Let x be in X, then E, the one point subset, is clearly connected, right? You cannot write a one point set as the disjoint union of two non-empty subsets, right? Is connected, and both X and X belongs to E, hence X is related to X. Symmetric, this is symmetric relation. Why is that? Well, let X, Y be in X with X is related to Y. Then there is a subset, there is a connected subset E of X with both X and Y are in X, not X, E. But then Y and X are also in E, right? This relation is clearly symmetric and E is connected, and thus Y is related to X. Okay, so whenever X is related to Y, Y is related to X. Therefore, it is symmetric. Reflexive, not reflexive, sorry, transitive or transitivity, transitive. Why it is transitive? Well, let X, Y, Z be in X with the following. X is related to Y and Y is related to Z. Okay, so we must show that X is related to Z. Well, X is related to Y means, by definition, there is a connected subset containing these 2 points. Okay, so there are connected subsets E1 and E2, so that X and Y belongs to E1 because X and Y are related, and Y and Z belongs to E2 because Y is related to Z. So I have these two connected subsets. However, these two connected subsets have a common point, namely Y, right? Since Y is in E1 intersection E2, and both subsets are connected, okay, connected, we see that their union E1, E2 is connected, right? If you have two connected subsets and if they have a common point, then their union is connected. And clearly X and Z both belongs to this connected subset, and hence X is related to Z. And this finishes the proof. Okay. So this is an equivalence relation. Hence, this is an equivalence relation. All right. Well, we know what? If you have an equivalence relation on a set X, then X can be written as the disjoint union of equivalence classes. All right. Let EX be this thing. All the elements in X. Okay, let me do it. For any X in X, let EX be the equivalence class of the relation containing the point X. So I have this EX is this. It is the set of all points in X so that X is related to Y. Okay, X is related to Y. This set clearly is connected. Why is that? Well, you see, so this is my next claim. EX is connected. Actually, proof is exactly this thing, but let me just do it. Why is that? Well, the reason is very simple. So X is here. For any Y in EX, you have some subset, right? Let's say EX containing both X and Y. Let me call this set EY. So X is fixed. For any Y, I choose some connected set containing both X and Y, right? Such EY exists because X and Y are related. Now this holds for all, okay, I should say not EY, I should say, okay, let me call this AY. For any Y, there is such a subset. So if you have another, let's say this is Y1, another Y2, then there is AY2. All these subsets are uh, connected and they have a common point, which is X. Therefore, their union is connected and their union, of course, lies inside EX because you know, any point here belongs to also this. So if I choose any other point here, it is also related to X because you know this subset AY1 is already connected and containing both these points. Okay, so that's the idea of the proof. Let me write this clearly. Okay, why this is connected. Okay. All right. Actually, okay, maybe I should write this. EX is the union of all connected subsets containing connected subsets of X containing X, in particular uh, EX is the largest connected set subset containing X. Well, let's see why this is true. So what is my first claim? EX is the union of all connected subsets of X containing X. All right. Well, let A be any connected subset. Of X containing X. Well, then for any Y in A, we have X is related to Y, right? Because A is a connected set containing both points. Therefore, hence, this Y is in EX. But Y was an arbitrary point in A, and that arbitrary point lies in EX. Therefore, A is a subset of EX. So, A is a subset of EX. But what we have seen is then, if you have any connected subset containing X, that lies inside EX. Therefore, EX contains all the connected subsets, and thus EX contains all the connected subsets of X containing little x. All right, let me stop here. In the second hour, I will finish the proof and then we will continue. Let me stop here now.